For this question, substitution is a good method to use to solve it. So we can use u is equal to the square root of x squared plus 4. Based off how substitution questions generally work, using u is equal to x squared plus 4 is probably also a good bet, but in this specific case, if you were to use u is equal to x squared plus 4, it wouldn't work. If you're not sure why, just try it out. You'll see you end up with something which is awkward to integrate. You'd probably have to use another substitution to figure that out. U is equal to root x squared plus 4 works quite nicely, though this is still quite a difficult question. So we first have to differentiate this. I'll rewrite the equation that we have there as u squared is equal to x squared plus 4. So then I can differentiate this implicitly. So u squared, differentiate u squared, becomes 2u. And then, because we're differentiating with respect to x, we then just chuck the du dx next to it. X squared becomes 2x, and then rearrange this for dx, and we end up with 2u over 2x times du, which is the same thing as u over x multiplied by du. Now we can sub this in, so we can sub in u is equal to this, and we can sub in dx is equal to u over x times du. So this then becomes the square root of u. I'm going to keep the x as is for now. The dx turns into u over x times du. This is the same thing as u squared over x squared du. And x squared, if we look at the equation that we have up here, x squared we can rewrite as u squared minus 4. So then this integral we can rewrite as u squared over u squared minus 4 du. Okay, so the denominator, u squared minus 4, can be rewritten as u minus 2, u plus 2. So we can use partial fractions to integrate what we have here. But before we do partial fractions, we first have to do long division, because this is an improper algebraic fraction. An improper algebraic fraction is when you have the greatest power on the top, in this case 2, being equal to or greater than the greatest power in the denominator, which is 2 in this case. So the order of this polynomial is 2, it's a quadratic. The order of this polynomial is also 2. When the order of the numerator is equal to or greater than the order of the denominator, that's when you have an improper algebraic fraction. That's when you then need to use long division. So u squared minus 4 divided by u squared. I'll put these placeholders here as well. U squared goes into u squared once. Put that up here. Times 1 by u squared minus 4. Take the two things away, we get a remainder of 4. So then, this fraction that we have over here can then be rewritten as 1 plus the remainder, 4, over u squared minus 4. And if you struggle to remember how to express this, or how to express this in this form once you've done your long division, think of this example. If we were to do 7 divided by 3, this is 2 1/3 as a mixed fraction, which is the same thing as 2 plus 1 over 3. So 2 is what's called your quotient. That's how many times 3 goes into the 7. 1 is your remainder, and then 3 is your divisor. So in our case, our quotient was 1. That's how many times u squared minus 4 went into u squared. Our remainder was 4. And our divisor was u squared minus 4. And that's exactly the order that we have here. We have to begin with our quotient, which is what we have there. Then we have our remainder. And then finally, we have our divisor at the bottom. Okay, so this is the same thing as the integral of 1 plus 4 all over u minus 2 times u plus 2. Now we can do partial fractions. So 4 over u minus 2 u plus 2 is the same thing as a over u minus 2 plus b over u plus 2. Make a common denominator, so left-hand side stays as is. The common denominator in this case would be u minus 2 u plus 2. And to get this to be the same as our denominator, we have to times the top and bottom of this fraction by u plus 2. So it'll be a times u plus 2. For this fraction here, we have to times the top and bottom by u minus 2 to get that common denominator. Denominators then cancel, and then we have 4 is equal to a times u plus 2 plus b times u minus 2. Now, let u equal to 2. That will make this bracket 0. We then end up with 4 is equal to a lots of 4, which gives a is 1. Let u equal to minus 2, and then we end up with, so that makes this bracket here 0. That makes this bracket minus 4. So we get 4 is equal to a times 0, so I'll just remove that term, plus b times minus 4. So this gives minus 4b is 4, which gives b is minus 1. So this integral, which I will call I, just to refer to it later, so I is now equal to, so we had 1 plus the fraction that we're splitting into partial fractions. So 1 plus, so if you look back to what we have here, we replace the a with 1, so 1 over u minus 2, and then we replace the b with minus 1. So this then becomes minus 1 over u plus 2. And now we integrate each term. So the 1 just becomes u. The second term, 1 over u minus 2, that becomes ln of u minus 2. Whenever we have something of the form of 1 over bx plus c, the integral of this would be of the form of ln of bx plus c. And then we just have to differentiate this to think about, does it give us exactly what we have here, or is it off by a factor? In our case, if we differentiated this using the chain rule, it would give you exactly this. So no need to put any kind of factor in front of this ln. Similarly, the second term would be ln of u plus 2. Again, no need to put any kind of corrective factor in front. This will differentiate exactly to give this using the chain rule. Plus c. Now I'll just combine these two logs using the division rule. So ln of one big modular symbol, u minus 2 over u plus 2. And the final step would be to replace the u with what we had it as in the first place, what our substitution was, x squared plus 4, root x squared plus 4. So this is then root of x squared plus 4 plus natural log root x squared plus 4 minus 2 on the outside of that, divided by root x squared plus 4 plus 2 plus c.